Now we should show that mu naught is a pre-measure. So I claim that mu naught, sorry, not mu naught, this is mu x cross y. So mu x cross y is a pre-measure on B naught. So to this end, let S be a union of Sn n equal to 1 to infinity, such that Sn belong to B naught for all n, and S also belongs to B naught. And supposing that these Sn's are disjoint, then we have to show that mu x cross y of S is equal to the sum mu x cross y of Sn n equal to 1 to infinity. So let us start with this following case. Suppose that each Sn is of the form a single Cartesian product En cross Fn, where En is in Bx and Fn is in By for each n, and then also that S is of the form E cross F. So since we have that E cross F is equal to the union of En cross Fn, this implies that the indicator function of E cross F x comma y is equal to the sum n equal to 1 to infinity of the indicator functions of En cross Fn at x comma y. But since we have a Cartesian product, chi E cross F is nothing but chi E x chi F y, and so this is for all x y in E cross F, of course, actually x cross y. So this is true for all x y in the Cartesian product, and we have this pointwise inequality, and now we can rewrite this as chi Ex chi Fy is equal to n equal to 1 to infinity chi En x chi Fn y. So note that all these chi E, chi F, chi En, chi Fn are measurable functions in their respective with respect to their respective sigma algebras. And now we are going to integrate this formula that we have here. So let's call this formula 1, and then integrating 1 with respect to mu y, what do we get? So we get integral over y chi E x chi Fy d mu y. So this is for y, and this is equal to the integral of the sum n equal to 1 to infinity chi En x chi Fn y d mu y. So the first, on the left hand side, this is simply, this is constant, and for this integral, so it's simply chi E x times the integral of chi F y, but this is nothing but mu y of f, And on the other hand, for the RHS, we have this is equal to by, so these are all non-negative functions, non-negative. So by Tonelli's theorem for interchange of summation and integrals, we have that this is equal to n equal to 1 to infinity integral y chi e n x chi f n y d mu y. So this is by Tonelli's theorem for interchanging integrals with infinite sums. So, but infinite sums of non-negative functions. So we have this, and now we can again simplify on the right hand side. So this is equal to chi e n x multiplied by mu y of f n. So then we again have this pointwise inequality chi e x mu y f equals the sum n equal to 1 to infinity chi e n x mu y of f n. And now we integrate with respect to x, integrating with respect to mu x. Now we get integral x chi e x d, there is a mu y f d mu x x is equal to the integral, again there is a sum n equal to 1 to infinity chi e n x mu y of f n d mu x, right? And then again we have on the left hand side, this is a constant and will come out of the integral, and then we only have mu x of e times mu y of f. And on the right hand side, again by Tonelli's theorem, we can interchange the integral and the summation sign to get integral of chi e n x mu y f n d mu x, but this is again nothing but mu x e n mu y f n. And since this was on the left hand side, we have mu x cross y of E cross f. So we have chosen our S to be of this simple form, and on the right hand side we have n equal to 1 to infinity. Similarly, mu x cross y E n cross f n, which was, these were all S n's. So we have shown this formula, that this formula holds when S n's have this simple form and S has this simple form. And now we can reduce the general case to this case as follows. Now suppose in general that S is equal to n equal to 1 to infinity S n, where S n belongs to Bx cross By for all n. This is a disjoint union, and further that S belongs to Bx cross By. Sorry, these belong to B naught, and again we have B naught. Now if we write S as a finite disjoint union Ai cross Bi, I equal to 1 to n, again a finite disjoint union. Of course, this Ai cross Bi, all these Ai's and Bi's belong to the respective sigma algebras Bx and By. So by finite additivity of mu x cross y, we have that mu x cross y s is equal to this finite sum I equal to 1 to n, capital N, ai cross mu x cross y ai cross bi. And now we can take for each n we can take the intersection of Sn with these elementary products. So it suffices to show again by finite additivity that mu x cross y ai cross bi is equal to the sum n equal to 1 to infinity mu x cross y Sn intersection with ai cross bi. So we have now reduced it to the case when S is a single elementary set, but on the right hand side these Sn's may not be single elementary sets, but since Sn belongs to this Boolean algebra B naught, then again we can have a decomposition of each Sn into finitely many pieces. So again write Sn is equal to En I, or rather Ein, or let me write Ejn cross Fjn j equal to 1 to Nn. So this is the number of terms may differ for different Sn's, but we still have a disjoint union of elements in B naught, and then Sn intersection ai cross bi is then a disjoint union of the form Gj cross Hj, j equal to 1 to some number m. So it holds, or rather we can write for some Gj in Bx for all j in 1 to m, and Hj in By for all j in 1 to m. So we have again used the fact that the intersection and cross product distribute over each other, and then we can write some disjoint union like this. On the other hand, then we have that mu x cross y Sn intersection ai cross bi is equal to the sum j equal to 1 to m mu x cross y Gj cross Hj, and so we are again reducing it to elementary sets of this form, and so therefore we have, so these are of course dependent on n, Gjn, and so mn here, Gjn's here, and they are also dependent on I. So we have to write everywhere n comma I. So everywhere it depends on n as well as I. Nevertheless, we still have this finite sum of elementary things, and so we have reduced it to the previous case where all the SNs were of elementary form in the product form, as well as this set S, which is the union, which is also the of the product form AI cross BI. And so we have already shown this to be true, and so the general case follows. The general case follows, and so this implies that mu x cross y is a pre-measure on B naught. So now the Hahn-Kolmogorov extension theorem, Hahn-Kolmogorov extension theorem gives us an extension which we still denote by mu x cross y on a sigma algebra on x cross y containing B naught, and this implies that since Bx cross By is the smallest sigma algebra containing B naught, this means that this mu x cross y, this extended mu x cross y, is a measure on Bx cross By, and it automatically satisfies the product formula that mu x cross y e cross f is equal to mu x e times mu y f, because it extends the same, because it is extending the mu x cross y, the pre-measure defined on B naught. And now for the uniqueness part, in fact this is where the sigma finiteness will play a part, and this is a general result that if x is sigma finite with respect to a pre-measure mu naught on a Boolean algebra B naught, which means that x is equal to the union, countable union of xj's in the Boolean algebra with mu naught of xj finite for all j, then any extension to a sigma algebra B containing B naught is unique, meaning that if nu is another, so let me call it mu here, and if nu is another measure on B, then mu equal to nu on B. So I'll just give a reference for this general result. You can try to prove it yourself, but you can also look at Foland's theorem 1.14, which gives a result, which gives a proof of this result. So we also have uniqueness in the sigma finite case.